Hello everyone, today we're going to start our brief introduction to carbohydrates. So carbohydrates are sugars, if you've heard of those. Things like glucose and fructose and sucrose and all those oses. So we're going to talk just a little bit about them to sort of finish up the semester. Not a whole lot of content, just 2 days of lectures. We're basically going to go through, and I want you to be able to recognize these kinds of things and sort of know just a little bit about the chemistry of these different structures. So if you look on the left, we've got, that's a monosaccharide in Fischer projection form, so we'll get used to seeing those. And then getting a little bit more complicated on the bottom right, we've got the closed form, and that's a Haworth projection is what it's called. It's the closed form of a different sugar, not this one on the left. So we'll see those. On the top, we've got a connection. That's a disaccharide that's showing the different kinds of connections you can make. And then on the right, that's a polysaccharide. That's actually starch. And so as you add in complexity, we'll talk about like what's important about those little details, okay? So let's go ahead and get started. So obviously we're going to start with the more simpler things. So we're going to talk about monosaccharides in the open form. They have several things that you'll need to look at. One thing is the functional group type. Another thing is the size. They are chiral, so we'll talk about D versus L. And then we'll talk about specific sugars that you'll see a lot. So like the sugars you'd want to kind of recognize and know. Some other things that we're going to sort of bring back that we've already talked about are Fischer projections and recognizing some key functional groups. So we've talked about Fischer projections, that was in section 2, and it was kind of like on the chirality stereochemistry section that we just mentioned, like there's chiral centers and that kind of stuff. So we'll just talk a little bit more about that. And then we want to make sure we can recognize the key functional groups of course, acetals and ketals, which we just talked about, but also hemiacetals and hemiketals, which are these abbreviations. So just as a reminder, Fischer projections are a way to draw things that have lots of chiral centers, generally speaking. So if you look at this thing on the left, this is the Fischer projection. Some people also call it the fishbone structure because it kind of looks like a fishbone, especially when we get more things going up and down. But they're always going to be sort of on their end like this. They're long and tall, not like flat. Generally, whenever you draw them, they're the highest oxidized form on the top. For us, that's always going to be an aldehyde. So if you look over here, it says CHO. You want to get used to seeing that condensed form version of an aldehyde, which if you look on the right, here it is the double bond O with an H on it. So that's the aldehyde functional group. CHO is just an abbreviated form. If you look on the far right, it says that. The other thing you may see sometimes is a carboxylic acid abbreviation. Oxidize it for different tests and things. So that's COOH is the same as a carboxylic acid, right? There's 1 carbon and 2 oxygens and a hydrogen, okay? The other thing is, whenever you're doing this, there's technically a code. So the things on the very top and very bottom, those things are dashed if you look at this structure here in the skeletal form. And then anything on the side is going to be wedged. So basically I think of it as it's constantly bending backwards and it's always trying to hug you because it's got the 2 things on the sides are like both coming towards you like they're trying to give you a hug. So think of it that way, and that sort of makes sense why we were never able to rotate around the bonds for Fischer projections or why it was hard to do RNS. We never did that. So it's just the way that they do it to keep it straight. Now this is made for sugars. Like this is the best thing about Fischer projection is it works really well for sugars, and we're going to see why. So just one more thing before we really dig into this, just a reminder, we're going to use Fischer projections for all the open forms of monosaccharides. So we're not going to use line bond for these. It doesn't work as well, and we'll talk about why later. So we're always going to use Fischer projections, so make sure that you feel comfortable with what those are. All right, let's talk about monosaccharides. The first thing that you would look at for a monosaccharide is what's the functional group. So we've talked a lot about different functional groups, and these are going to be ones that we already know. Basically, it's going to be, does it have an aldehyde or a ketone as the double bond O? Now, the thing is, it is drawn in a different way, right? So if you look on the left, there's an aldehyde. And where did we say that was? It's on the top, right? The CHO is the abbreviation. If you look on the right, where is something that's a ketone? Right, it's at carbon 2. So for this one, it's actually in the middle and they draw out the carbonyl. But whenever it's on the top, they just don't draw it out because everyone knows that abbreviation and it's just the standard form for Fischer projections, okay? So generally, if you have something that has an aldehyde, but it's a sugar, that's the ose part, it's called an aldose. So if you look here, erythrose is an aldose. If you look on the right, if it's got a ketone in it and it's a sugar, then it's going to be a ketose. And that's basically what you need to know. So you don't have to know these specific names. You just want to be able to recognize if it's an aldose or a ketose. Another thing that can be discussed about sugars is their size, and they've just made different names for those. So as you can see, we have some sugars of various sizes. The names of the sizes are at the top. So you could have a triose, a tetrose, a pentose, a hexose. Those are the ones you'll normally see. And they're pretty easy. They're just prefixes that you would have for the numbers. So if you look at the very first one, it's called a triose because it has 1, 2, 3 carbons here, right? This one also has an aldehyde group, so this would be called an aldotriose. So it's got the aldehyde up here, so that's the aldo part. All right, so pause the video and name the other 3. So name if they're aldose or ketose, and then what number of carbon it has. All right, so looking at these, this should be what you got. Make sure you double check your answers on that, but generally this is pretty straightforward. So if you have any questions, just let me know, but I'm not going to go over it anymore in this talk. I do want to note, however, that this very last one is fructose. It's a very important ketose that we'll talk about. Generally, the only ketose we really talk about is fructose, so that's when you see a lot. So I just wanted to make sure you recognize that one. So what are the sugars that I really want us to know? We're going to focus on 5 of the monosaccharides. So the ones that we need to know are glucose, mannose, galactose, fructose, and ribose. These are ones that you'll see pretty often in different formats. You may start to see them when we have sugar pieces on DNA and things like that in biochemistry, things like that, things that you're going to want to know for biochemistry stuff. Generally, we're going to focus on the D form because that's the natural form that you see the most often, but we'll also talk about what the L form is. So when we're talking about whether a sugar is D or L, we're talking about the enantiomer. So we said before that lots of molecules in your body are chiral, and sugars are no exception. They're also chiral. So to determine if it's D or L, we're going to just have a set thing. So if you look here, it says, look at the C5 from the CHO, that's C1, and then C5 would be here. And then you're going to look and see if that's to the right or to the left. So if the OH is to the right, then that would be the D form. So as you can see, this one on the left is going to be the D form of glucose. Then the L form, it's not just switching the C5. Like if you look at the C5, clearly that OH is on the left. But if you look, the whole thing is reversed. So it's an enantiomer, meaning the mirror image. So when you're trying to convert something from D to L, you can't just change C5. You have to change the whole molecule so that it makes a mirror image. That's something that I messed up a little bit whenever I first took biochemistry. So I just want to make sure I pointed that out. The whole thing about D or L sugars also brings into point why we're using Fischer projections. So when you use a Fischer projection, it's very easy to just say it's on the left, it's on the right, because the whole molecule is drawn as flat, and we just assume that the flat means a specific thing that we talked about earlier. But if we were to draw these in like normal line bond form, we would have to go and say each one, like, is this R, is this S? Well, it kind of depends on what's on the bottom and what's on the top because there's lots of CHOs, right? So it could get really confusing really fast. But using the Fischer projection where everything's flat makes it really easy to see D or L because you just count down from the top and you know what you're looking at. So yay for Fischer projections. I hope you're glad that you learned them now, even though at the time when we talked about them, I'm sure you were like, why do we need to know these? But that's why. So the question is, how do we know that these things are chiral? Well, actually, we didn't talk about this a whole lot before, but they use this thing called plane polarized light to determine that. You can see this picture on the right, but basically what's happening is they're taking a certain direction of light. They line it up, like they put a slit and it goes through the slit, so it's all lined up the same direction. And then when it goes through a solution, the line will curve either to the left or to the right, clockwise or counterclockwise. And then they measure the angle of that change. So if you look here, they've got glucose here towards the bottom, and they say it has a positive specific rotation, so that means if it's clockwise. And then if you've got fructose, it's got a negative specific rotation, and that's counterclockwise. And the numbers are not really something you can predict. That's something that's an experimental property. So that's just based on what the molecule is itself. But that's sort of how they can tell, and that's also they can tell how pure it is based on the known number being, say, plus 52.7. If it's not 52.7, if it's like slightly different, that means you may have some more of the L form in there, like they're mixed together. And then if the rotation is 0, that's when we talked about racemic mixtures. That's what they are. They measure a 0 specific rotation because for every one going to the counterclockwise, the other one's going clockwise. So that's just a little bit about optical rotation, since we didn't talk about it before. So at this moment, let's just sort of pause to check our understanding. What type of sugar do we have here on the right? So you don't have to know the name of it, like if it's like glucose or something. You just have to identify if it's one of these different types. So pause the video and do that. All right, so is this what you got? Right. So then hopefully that makes sense. If not, just let me know or look up, go back and review the other material and see if you can figure out why it's that. Before we move on, I also want you to practice drawing the opposite version. So remember we said this is the L version, so please draw the D version of this molecule on your paper. Pause the video to do that. All right, so if I do that, I'm going to basically draw the same chain, right? I'm going to draw the same top and bottom, and then if it's D, what does that mean is going to be different? Right, it's going to have the C5 with the OH on the other side. It's going to be on the right instead of on the left. So I draw that first. And then how do I know what to draw in this one right above it, this OH that's on the left? Should it be on the left or the right? Right, it's going to be on the right also because we're just doing a mirror image. So then we'll just go up the chain and then we should get our answer. All right, so that's it for the basics of the first part of monosaccharides where they're all in the open form. But we are going to talk about one more thing before we get to the closed form. So make sure that you watch the next video. Thanks, bye.